When a large language model answers a question, it appears to reason, but beneath the chat interface, there is no conscious thought. Instead, the physical reality of artificial intelligence is a probabilistic engine operating on cascading arrays of floating point numbers. To understand how these numbers approximate human logic, we can look at Andrej Karpathy's nanoGPT. nanoGPT is a pedagogical framework that deconstructs OpenAI's GPT-2 architecture. It strips away heavy enterprise software wrappers to expose the exact mathematical operations that make sequence prediction possible. We are going to trace the exact mechanical life cycle of a single word, apple, as it travels through this architecture. We will follow it from a raw text input down into a geometric space and out as a fully contextualized prediction. Our target sequence is the phrase, the red apple. The model's singular objective is to calculate the most statistically probable next word to follow that sequence. Treating these models as decountable geometric engines allows for precise engineering. When we move past the idea of a black box, we can identify the specific mathematical bottlenecks that inhibit performance and scale. The first computational barrier in language modeling is translation. Machine learning algorithms cannot process letters or words. Discrete linguistic symbols must be mapped into a continuous numerical space before any processing can occur. Early baby GPT experiments attempted character-level modeling, assigning a unique integer to every individual letter and punctuation mark in Shakespeare's texts. While this requires a tiny vocabulary of about 65 tokens, it lacks semantic density. The model's limited memory window fills up with individual letters rather than meaningful concepts. Modern models solve this using byte pair encoding, or BPE. BPE is an algorithm that iteratively merges the most frequent pairs of characters into new, larger subword units. This balances a manageable vocabulary size with high context efficiency. In our target sequence, the BPE tokenizer evaluates the word apple and translates it into a distinct integer ID. For GPT-2's vocabulary, that ID is 17493. This integer acts as a strict lookup index in the embedding layer. The model searches its initial weight matrix and extracts the 17493rd row. For a model like GPT-2 Small, this row is a continuous 768-dimensional vector. This high-dimensional space establishes the geometry of meaning. During training, the model learns to position these vectors so that semantic similarity translates directly to geometric proximity. The vector for apple will exhibit a high cosine similarity to the vector for pear. At this stage, the model only has isolated definitions. It doesn't know the sequence order. Without sequence, the dog chased the cat is mathematically identical to the cat chased the dog. To solve this, we inject positional encodings, either learned vectors or rotary mathematical angles that embed the specific index position into the data. Because apple is the third word in our sequence, we retrieve the positional vector for index 2. We mathematically add this position vector to the apple embedding vector, locking in its place in time. Human semantic meaning and temporal sequence have now been successfully translated into spatial computable geometry. The apple vector is ready for processing. Early language models relied on the bigram baseline. A bigram model operates on the Markovian assumption that the probability of the next token depends entirely on the single preceding token. It structurally lacks the ability to aggregate historical context, meaning it forgets the start of a sentence by the time it reaches the end. The transformer architecture bypasses this limitation using self-attention. Self-attention is a dynamic information retrieval protocol that allows every token in a sequence to communicate and build a contextualized representation of the input. It accomplishes this through the query, key, and value framework. Every token in the sequence is multiplied by learned weight matrices to generate 3 distinct projections. The query vector acts as a request, asking, "What am I looking for?" The key vector acts as a broadcast, stating, "What information do I contain?" Our Apple query evaluates the keys of the previous tokens. The network calculates the dot product between the query and the keys. This mathematical multiplication acts as a matchmaking operation, outputting a compatibility score. Because red is an adjective modifying a noun, the Apple query and the red key produce a very high score. The third projection is the value vector. The value contains the actual semantic payload that a token will share if its compatibility score is high enough. The high attention score scales the value vector for red. This scaled payload is then mathematically added directly into the apple vector. Apple is no longer a generic noun. Its geometry has updated. In a decoder-only architecture trained to predict the next word, we encounter a structural hazard. If Apple were allowed to generate a query that looked ahead at the key of the token we are trying to predict, the model would cheat during training. We prevent this using causal masking. Causal masking applies a lower triangular matrix of negative infinity to the attention scores. This zeroes out future tokens, ensuring information only flows from the past to the present. Through self-attention, the apple vector abandons its isolated dictionary definition. It has aggregated its surroundings, becoming a specific, context-aware geometric entity. A single attention mechanism can only focus on one type of relationship at a time, but processing language requires tracking multiple dependencies, like local grammar and long-range pronoun references, simultaneously. We solve this with multi-head attention. The original embedding dimension is split into parallel subspaces. Each head generates its own independent queries, keys, and values, allowing the model to capture different semantic perspectives at the exact same time. However, attention alone is just a sophisticated communication protocol. It re-averages data, but it does not execute complex logic or retrieve learned facts. For that, we route the vector into a position-wise feed-forward network, or FFN. The FFN is a set of isolated linear layers applied identically to every token to process and transform its representation. Inside the FFN, the vector undergoes an expansion phase. A linear layer projects it from its base 768 dimensions into a vastly larger hidden dimension, typically 4 times its size. This wide representation space allows the model to untangle complex overlapping patterns. Here, we apply a nonlinear activation function, like GELU or squared ReLU. These mathematical curves zero out negative values and scale positive ones, breaking the linearity of the matrix. This nonlinearity is what allows the network to approximate complex human logic. Finally, a compression phase projects the processed vector back down to its original 768 dimensions so it can continue through the architecture. The feed-forward network takes the context gathered during the attention phase, applies deep reasoning, and actively updates the token's internal state. Stacking these attention and feed-forward layers creates deep neural networks, which introduces the vanishing gradient problem. As data moves through dozens of layers, the mathematical signal used to update the weights becomes increasingly small and noisy, stalling the training process. nanoGPT maintains stability using residual connections. A residual connection is a structural bypass that takes the unmodified input of a layer and mathematically adds it directly to that layer's output. This creates a persistent residual stream flowing through the entire depth of the model. The sublayers no longer have to learn complete representations from scratch. They only need to learn the incremental updates required at their specific stage. To keep the math stable as these updates stack, the model applies layer normalization. Layer norm adjusts the distribution of activations across features, ensuring the data doesn't spiral out of proportion. It also forces directions in the geometric space to align with specific interpretable concepts. With the architecture stable, the bottleneck shifts to physical compute. The nanoGPT speedrun project focuses on hardware optimization, aiming to execute these matrix calculations over 600 times faster than the original 2019 benchmarks. One major speedrun optimization is the muon optimizer. In standard networks, weights can become correlated and redundant. The muon optimizer forces an orthogonalization step during training. This ensures that every dimension in the weight matrix is learning a distinct non-overlapping feature, heavily reducing wasted compute. The other massive bottleneck is memory bandwidth. Calculating self-attention requires an n-squared matrix size. Writing that massive grid to a GPU's standard VRAM is incredibly slow. Modern implementations use Flash Attention 3. Flash Attention is a hardware-aware algorithm that restructures the math, keeping the attention matrix entirely inside the GPU's ultra-fast on-chip SRAM memory. High-performance machine intelligence relies on the alignment of mathematical theory with bare metal hardware constraints. After successfully passing through 12 layers of attention aggregation, nonlinear reasoning, and residual updates, our apple vector reaches the end of the transformer block. In the unembedding phase, multiplying the final vector by the transposed embedding matrix projects the 768 dimensions outward. This generates raw prediction scores, logits, for all 50,257 tokens. Softmax then converts these into a probability distribution, summing to 100%, heavily favoring the word fell. We can control how the model selects its next word using autoregressive sampling parameters. If we adjust the temperature, a parameter that scales the logits before the softmax, we can either sharpen the distribution to guarantee the most likely word, or flatten it to allow for more creative selections. We also apply top K filtering. Top K is a safeguard that drops all but the highest probability tokens, preventing the model from sampling the long tail of impossible continuations created by softmax noise. The prediction is finalized. The model samples the word fell and commits it to the text sequence. Through the autoregressive loop, fell immediately becomes the new input token, and the sequence begins again. The capabilities of a large language model are emergent. By reducing the system to its first principles, we find a sequential engine of matrix multiplications and communication protocols. Deconstructing these foundational atoms allows engineers to identify the specific levers for optimization and scale within the transformer architecture.